So, learning target number 2. I can describe the relationship between force, mass, and acceleration. Okay? And can correctly determine an object's weight and measure the physical properties of force. Okay? So first thing, we have an experiment going on where we're going to apply a force, and we're going to apply the same magnitude of force to two different objects. One of the objects is 10 times larger than the other one. Okay? And if we graph the acceleration versus force as we, increase that force, these are the data points that we're given. So you don't have to calculate this. This is just given to you, okay? And it's seen that the slope of this line for object B was 1 over m, and the slope of this line is equal to 1 over 10m. Okay, and so here's how this data can help us. We know the equation for the slope of a straight line. We know that's y equals kx plus b, where k is the slope of that line. So we can start plugging in these values. We can say my y value is acceleration. Okay? And my k value for this one is 1 over m. And then my x value is force. And then plus b. B is the y-intercept, and it's intercepting at 0. So we can rearrange this to say acceleration is equal to the force divided by the mass, or force is equal to mass times by acceleration. And that's our big equation that we're going to be using. It's Newton's second law. So what can this equation tell us? Well, first off, if we have an object and we're applying two forces to that object, I would take the addition of those two forces to tell me what that overall net would be. Okay? And we know that force is equal to mass times by the acceleration. So if an object has mass and a force is applied, then it's going to be accelerating. Okay? And this is specifically our net force there. Okay? This also shows mass is going to remain the same. But if we double our force, then our acceleration would double as well. And so when we look at this one, we have 100 newtons of force to the right, 100 newtons of force to the left. And so this is what my free body diagram would look like. And so I'm going to choose to the right to be positive. So I'd have a positive F1, and I'm adding that to a negative F2 because it's in the negative direction. So that would be 100 newtons minus 100 newtons. And so my overall net force, adding them together, is just 0 newtons. So when my force is 0 and we have some mass, then the acceleration is 0 as well, because we need 0 acceleration, 0 times by anything will equal 0. Okay? Now here the forces are not being applied evenly. We have 100 newtons in the positive x direction, and we have 200 newtons in the negative x direction. So if I were to add those together, I'd say my force is in the x direction. I have a positive 100 newtons, and then I'm going to add that to a negative 200 newtons. And so my overall would be negative 100 newtons. That's my overall force. All these combined result in the same thing as me just applying a negative 100 newtons in the x direction. So what I'm doing there is I'm figuring out the sum of my forces. Okay, so that's what this symbol means. It means sum. And so I like to figure out the sum of my forces in the x direction and then the sum of my forces in the y direction. Now, if your sum of your forces in both the x and the y equals 0, then the object is static, which means that it's either moving with a constant velocity of 0, stationary, or it's moving at some constant velocity. When an object does not equal, or sorry, the sum of the forces does not equal 0, whether in the x, the y, or both, then it's dynamic, which means there's some form of acceleration happening. Another way of rewriting that original equation was the overall sum of the forces is going to be mass times by acceleration. Okay, so we have a couple examples here. Two horizontal forces, 225 newtons and 165 newtons, are exerted on the canoe. If these forces are applied in the same direction, what is the net force? Okay, so we have our canoe, okay, and we have these applied forces. So I'm going to represent the canoe with a dot, and we have 225 newtons, and then we're also going to have another one which should be smaller. I shouldn't make them the same size, so just be aware of that. At 165 newtons. So the sum of my forces in the x direction would be the 225 in the positive x plus the 165 in the positive x. So 225 plus 165, 390 newtons. So that's the sum of my forces. Okay. Suppose the same two forces were applied to a canoe in opposite directions. So when we have them in opposite directions, let's put the 225 in the positive x, and then we'll put the 165 in the negative x. Okay. Sum of my forces in the x direction will be my positive 225 newtons plus, because this is sum, so we're adding them all together, so plus my negative 165 newtons, and it's negative because it's a vector and it's in the negative x direction. So 225 minus 165, that gives us 60 newtons in the positive x direction. And I can draw this. I can show here with this 390 in the positive x, I can show that my overall force net is like this, okay, with a magnitude of 390. And then here, I can show that my overall force net is still in the positive direction, but it's much smaller for this situation. While at a family reunion, you decide to have a tug-of-war. You and your cousin decide to challenge your cousin's sisters and brother. You pull east with a force of 35 newtons, and your cousin pulls east also with a force of 42 newtons. Your cousin's sister's brother pulls west with a force of 54 newtons. What is the net force of the tug-of-war? Okay. The net force of this whole system of the tug-of-war. We have You pull east 35 newtons. Your cousin pulls east also with a force of 42 newtons. Your cousin's sister's brother pulls west with a force of 54 newtons. What is the net force of this tug of war? Well, that would be the sum of the forces in the x direction, which would be a positive 35 newtons plus a positive 42 newtons, and then plus a negative 54 newtons because it's going in my negative x direction. Okay. So we're going to take 35 plus 42 and then minus 54, and that leaves us with a positive 23 newtons. Okay. Now I can redraw this. I can say this overall net, this is exactly the same as if we had a tiny little force net, which was 23 newtons. Okay. Newton's second law. Let me see where we're at on time. All right, let's talk through it. Whenever forces are unbalanced, okay, and this right here, an acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Okay, this is Newton's second law. Force equals mass times by acceleration. So if we want to solve for acceleration, we would just divide by mass. So acceleration is equal to the force net divided by the mass. Okay. What was said here was just represented there. If you understand this equation, then you're good. Forces are unbalanced. Okay, so which means we have some net force, that it's not equal to 0. Then there is going to be an acceleration as long as there's a mass, which there always is. So an acceleration is directly proportional to the net force, or the acceleration is inversely proportional to the object's mass. Both are true, right? Because that's what you see. Acceleration is directly proportional, and acceleration is inversely proportional. So directly proportional to the force, inversely proportional to the mass. Now let's think through what we mean by that. If acceleration is larger and our mass stays the same, then our force is going to get larger because they're proportional. If one goes up, the other one goes up. Okay, and checking time. Mass is inversely proportional. So if our acceleration got bigger and our force stayed the same, then the mass had to get smaller. Okay, inversely, one goes up, the other one goes down. So if we have some mass and we're applying some force, and then we double our force, but the mass stays the same, this would double. It's proportional to acceleration. Acceleration also doubles. Let's start our next video on this one.